All right, the first illustration of Stokes' theorem is question 1. It says let f be yi minus xj plus 3k, and let c be the circle of radius 2 in the xy plane centered at the origin with a counterclockwise orientation. Okay, so here's our circle C, radius 2, centered at the origin with a counterclockwise orientation. And our job in part A is to compute the line integral of our vector field f over this circle C. And we're asked to do this directly by using an appropriate parameterization of C. So I'll go ahead and parameterize circle C in the usual ways, right? 2 cosine t, 2 sine t, 0. T varies from 0 to 2 pi, so that's going to give us a counterclockwise orientation of this circle. And here's the tangent vector, r prime of t. It's really just the velocity vector as we move along our path. So it's negative 2 sine t, 2 cosine t, 0. Okay, so now recall that to compute a line integral such as this, we want to take the dot product of the vector field f evaluated along our circle, so that's the f of r of t vector, and we're dotting that with this green tangent vector. Okay, and we're going to integrate that dot product from 0 to 2 pi. So we'll go ahead and punch those in. So for f of r of t, well, the I component of our vector field f is y, and along the circle, y is 2 sine t. So we have 2 sine t then for the I component. For the j component, we have minus x, and x is 2 cosine t, so that's going to give us a negative 2 cosine t for the j component. And then the k component of the vector field f is just constant 3, so that's 3 here. We're dotting that with this green tangent vector. Okay, so when you take this dot product, it's pretty nice. You get minus 4 sine squared minus 4 cos squared plus 0. So through the Pythagorean identity, we just get negative 4, and then integrating that from 0 to 2 pi gives us a value of negative 8 pi. All right, cool. So that is the line integral. And now for part B, it says compute the surface integral of the curl of the vector field, right? This is the right side of Stokes' theorem, over the following surfaces directly by using an appropriate parameterization of each surface. All right, so make a little space here. And so first off, we'll go ahead and just compute the curl of this vector field. And it's pretty nice here, right? The I and the j components are just 0, and the k component comes out to be constant negative 2. Okay, so that's really nice. Now for part 1, s is the part of the paraboloid. Z is 4 minus x squared minus y squared above the xy plane oriented, so normal vectors point upward. Okay, so first note that the intersection of this paraboloid in the xy plane is this circle C, right? Because if Z is 0, we get x squared plus y squared is equal to 4, and that's just the circle of radius 2 centered at the origin in the xy plane. Okay, so C is the boundary of this surface we're considering. And since we are orienting the surface so the normal vectors point outward, right, through our right-hand rule convention, the orientation of S and the boundary curve C are compatible. All right, cool. So now the surface is given in explicit form. It's just Z equals this expression here, 4 minus x squared minus y squared. So I'm going to use an explicit parameterization of the surface. So recalling from the last section, this is just r of xy is x comma y comma 4 minus x squared minus y squared. And to find the normal vector tx cross ty, right, this is just direct from the table in the surface integral worksheet, right? If I call this expression 4 minus x squared minus y squared g of xy, then that cross product of these tangent vectors, so in other words, this normal vector is minus gx minus gy 1. So for this particular function, we'll get 2x, 2y, 1. And now to compute the surface integral, okay, so this is where we take the vector field, right, we're integrating, and evaluate that along our surface. Okay, so here we're going to take this curl vector field and evaluate it along our paraboloid. and then we're going to dot that with this normal vector, tx cross ty, and we're going to integrate this dot product over the region R in which we're letting x and y vary. Okay, so if I project the paraboloid onto the xy plane, okay, we can see that we're letting x and y vary over this disk of radius 2 centered at the origin. All right, so go ahead and punch all that in. So since our curl in this case is just a constant vector, right? Evaluating that along the paraboloid, well, it'll just still be that constant, 0, 0, -2. Okay, so we have that, and then tx cross ty, we computed up here, so that's our 2x, 2y, 1. And now we're going to integrate this dot product over the disk of radius 2 centered at the origin. And notice this dot product is just -2. So if I integrate a constant over this region R, that's just going to be -2, that constant, times the area of R. And since this is just a circular disk of radius 2, it has area 4 pi. So we get -8 pi for the value of this surface integral. Okay, and that's exactly what Stokes' theorem says we should get, right? It's the same value as the line integral over the boundary curve that we found in part A. Okay, so again, the circulation across the surface S, right, we're finding is equal to the circulation of the vector field along that boundary curve. Cool. All right, so now let's go ahead and look at the next part. Here, our surface is the upper hemisphere of radius 2, centered at the origin, and it's oriented so normal vectors point upward. Okay, so here is our surface, and again, since we're using these upward pointing normals, the orientations of the surface and the boundary curve are compatible. All right, now I'm going to go ahead and use the parameterization that we derived from spherical coordinates in the last section. Again, this is just straight from the table. Here, A is just the radius of the sphere, remember, and so that's just 2 in this case. So we have 2 sine u cos v, 2 sine u sine v, and then 2 cos u. And u, which is really the angle phi in spherical coordinates, that varies from 0 to pi over 2 in this case, right? Because when we're 0, we're along the positive z-axis, pi over 2, we're in the xy plane. And then v, which is just the polar angle theta, that varies from 0 to 2 pi. And our normal vector tu cross tv, again, just straight from the table, that's going to be 4 sine u, where 4 here is really a squared, and a is 2, remember. So 4 sine u, and then we have this vector, which is really just the unit vector in the direction of r of u, v. So that's just sine u cos v, sine u sine v, and cos u. All right, so then to compute the corresponding surface integral now, well, we're going to take the curl vector, which again is just constant, evaluated along the hemisphere. That's what this part is doing. And then we're dotting that with this normal vector, and we're going to integrate this dot product over now this rectangle R, right? These are the bounds on u and v. So this is happening in the uv plane. All right, so again, our curl vector being constant just gives us 0, 0, -2. And I'm going to go ahead and make a little space there because that long normal vector there in orange, right? So I dot that with tu cross tv, that's right here. And this is, again, a pretty simple dot product. The 4 sine u is multiplying the cosine u. And since I only have a non-zero k component there for the curl vector, I'm going to get a -8 sine u cos u. And we're going to integrate this expression as we let u vary from 0 to pi over 2 and v varying from 0 to 2 pi. So the v integral, that's just going to pick up a factor of 2 pi, right? Because the integrand is independent of v. And so we get 2 pi times, well, this integral, you could use a substitution, but also just noting that cosine of u is the derivative of sine, we're going to get, ignoring the -8 for the moment, 1/2 sine squared of u. So then the -8 multiplying the half will give us a -4 out in front. And so we evaluate and voila, well, we get negative 8 pi again. And that's exactly what Stokes' theorem says. It says, right, the net circulation over this hemisphere of our vector field, right? This is going to equal the circulation down here on the boundary curve. All right, very nice. And then for the very last part, this is, I'll bring up the statement again. S is the disk of radius 2 in the xy plane centered at the origin, so normal vectors point upward. Okay, so now we just have this flat surface, right? It's just the disk enclosed by C. All right, so the normal vector, well, that's just the unit normal vector now, n is just k, right? And that's going to be the same unit normal direction there at all points because we're looking at just this flat surface. And by our right-hand rule convention, right, this choice of upward pointing normal is compatible with the orientation on our boundary curve. And so here, I mean, I could go ahead and parameterize this surface using, say, an explicit parameterization, but we can actually get away with doing less. Just notice again the fact that the normal vector is just k at every point on our surface, and our curl vector is just constant. If I dot these two vectors, right, k, remember, is just 0, 0, 1, so I'm going to get a dot product of a constant negative 2. So if I integrate this dot product over our surface, which is just this flat disk, I'm really just integrating the constant negative 2. So that's just going to be negative 2 times the area of that disk, and hey, again, I get negative 8 pi as Stokes' theorem promises, okay? Now, one final comment here, actually two final comments. In this example, this is really just Green's theorem. So in the intro video, I said that Stokes' theorem, right, is a three-dimensional version of Green's theorem, where Green's theorem really is just a special case of Stokes. Well, here, right, this, if I just think about this as living in the xy plane, if you do the corresponding calculation, okay, this dot product right here, the negative 2, okay, notice it's just the k component of the curl vector. And in our discussion of curl in section 15.5, that is our del q del x minus del p del y. So this is really just the 2D curl, and we're just integrating the 2D curl there over this region, and in this case, it turns out, of course, to be negative 8 pi as expected. But yeah, the point is this is really just Green's theorem at this point when you're looking at a flat surface like this sitting in the xy plane. Okay, my last comment is that what we also have seen is that all three of these surfaces, right, the paraboloid, the hemisphere, and this flat disk, they all have this common boundary curve, okay, and the surface integral, right, of the curl has turned out to be that common value, which is equal to the line integral. Now, a really powerful consequence of this is that, look, this surface in principle can be anything you want it to be. Okay, so we're going to take advantage of this in problems to come, where if this surface up here is really crazy, we can trade it in for something less crazy, and that might be to our advantage in that, you know, making a different choice of surface could lead to a much simpler calculation. Okay, so this observation actually is one of the really, really powerful consequences of Stokes' theorem, as we'll see. So we'll get into that more later. That will do it for this problem. Thanks so much.